Hello and welcome to the UIC podcast.
Thank you. I
Uh,
appreciate it.
for our listeners and viewers, can you say your name and where you work?
So my name is Ashlee Howarth, and I'm an associate professor at Concordia University, which is located in Montreal, Canada.
Great. And what do you do there?
So I'm an associate professor, which means that my job is split into three components. 30% is research, 30% is teaching, and 30% is service to the university and to the greater chemistry and scientific community. And specifically, I'm an inorganic materials chemist. Um, so I work on making new materials, inorganic materials, for wide-ranging applications, things like wastewater treatment, nuclear wastewater treatment, the detoxification of chemical warfare agents, drug delivery, sensing, bioimaging, X-ray detection, kind of you name it. We work on a lot of different applications of our material.
That is amazing. So, with the materials that you're making, do you have to have samples of nuclear wastewater in your lab?
So we mostly make samples ourselves that are
Okay.
not actually radioactive.
Okay.
So we make the samples up with all the same components that we know is contained in the nuclear waste,
Okay.
but with the elements in the non-radioactive form. So
Okay.
that's much safer and much
Sure.
easier to work with, but they have all of the same reactivity in terms of the way they would interact with our materials or in terms of the way we would absorb them or degrade them. They have mostly the same reactivity in that sense. It's just that they're not radioactive.
Gotcha.
Yeah.
Gotcha. And then what about the chemical warfare agents?
Yeah, so that's a good question too. So we also do not work with real chemical warfare agents in our lab at Concordia, although in the past I have collaborated with researchers at the US Army labs where they have actually tested our materials with real chemical warfare agents in their labs down just outside of Washington. Um, but in our lab, we use a simulant molecule. So these are molecules that look very similar to the real chemical warfare agents. They might just have one atom that's different, but they have similar reactivity in that, you know, if we're able to make a material that can detoxify or degrade the simulant, then we're pretty sure it will work the same way on the real agent. But they're much safer and easier to handle. So there's always some toxicity associated with them, of course, much like any chemical we work with in the lab, but not the same degree of toxicity or danger that's associated with the real agents.
That is really, really cool. And it sounds like it's much safer for you and everyone else in the lab.
Yes, definitely. Much safer to work with the simulants or to work with kind of simulated solutions of nuclear waste, for sure.
Yeah. Yeah. You wouldn't want to have a cell explode and get nuclear wastewater on your clothes.
Exactly.
Um, so what are you working on in your lab right now?
Um, so that's a good question. So right now there are 10 graduate students in my lab. So that's 7 PhD students and 7 master's students. And every student has their own unique projects. And so because of that, there are 10 different things I could tell you about. Um,
Okay.
but a lot of what we do is materials discovery. So we work a lot on making new materials, and specifically the materials are metal organic frameworks or MOFs. And so my students, all 10 of them, no matter what project they're working on, they spend a lot of time designing and trying to synthesize these new materials with properties that we design into them that we hypothesize will be useful for whatever their end goal is.
Okay.
So in a lot of cases, their end goal is catalysis. So to catalytically degrade, like I said, chemical warfare agents, or to catalytically degrade different harmful contaminants in water. Um, some of their end goals would be absorption of different contaminants, either from water or from air. So it could be air pollutants as well. Some of their end goals are water harvesting applications, so also absorbing water from the air so that we can harvest water in dry or in humid conditions and then use that water, for drinking water to have
That
safe
is so
drinking
cool.
water. Yeah, basically anything you can imagine a sponge being used for, these are like molecular sponges, right? So anything you can imagine a sponge being used for, we try to use our materials for that.
That is so neat.
Yeah.
And now, are these materials, are they manufactured at the university as well? Or are they just designed there?
We design them and we do synthesize them, but in our labs at Concordia, because we're academic research labs, we typically make them on a small scale. So we make
Uh-huh.
like 30 to 100 milligrams of
Okay.
materials. That's like a maximum of zero point 0.1 gram of material, right? So
Mhm.
like less than a sugar cube
Sure.
worth of moth, basically. That's the scale we typically make them on, because it's fundamental research. But there are companies out there making them on a much larger scale, like kilogram and ton scale, including Numat Technologies, which is actually in Skokie, Illinois. So I think
Oh, that's right by us.
and BASF, which has different locations in a lot of places, mostly in Germany, and also Sponte, which is a company in Canada. So there are companies making them on a much larger scale, but typically at the university, we do things on a much smaller scale. It's more cost effective and more environmentally friendly to do discovery research on that scale too.
Sure. So you guys would do proof of concept, and then, uh, do you have anybody else replicate your experiments? Because I know with the, scientific process, you want replication.
Yeah, that's a really good question. So, usually we first start by just making sure we can replicate the experiment within our own lab and within our
Okay.
own team, right? So, one student will run an experiment or maybe discover a new moth, discover a new synthetic procedure, and then some of the other students in the lab will try to replicate that just by something that's written down on a piece of paper, not with
Yeah,
the actual student helping them, right?
great.
And then we normally get some sort of external validation through collaborators, either academic collaborators or industrial collaborators who will also try to make the same materials that we make in their own labs, and they'll give us feedback on how that went. Or sometimes it's not even collaborators, but we'll see people citing our research and saying that they used our procedure. So then
Cool.
we'll know that it works in another
Yeah,
lab. So yes, reproducibility and that sort of validation is definitely important.
that is always so exciting when you get some input out of left field saying, "Oh, hey, we used their stuff and it totally worked."
Yeah, it's really exciting, especially if it's researchers that you maybe know or you've heard of, but you've never actually met them, and then you find
Sure.
out that they've been reading your work and they're using your procedures or your methods to do something. It's really exciting for me and for the students that develop the procedures too.
Absolutely.
Mhm.
I'm, uh, I'm still new to this whole sphere, but I'm getting academic papers popping up showing when our machines get used by different, scientists, and it is so cool seeing our stuff being used in Antarctica or being used in, coal-powered coal-powered plants in China, and they're measuring the carbon and all sorts of other stuff in the potash at the bottom of that. And then you've got people who are pruning guava trees and then taking the prune waste, just extra limbs, turning them into pellets, and then examining how effective and clean those are as an energy source. And our stuff gets used for all of that, which is so cool to me because it's still new to me.
Yeah, that's awesome. It's also cool to think that you like designed a piece of equipment and now people are finding all these uses for it that you probably didn't even think about or couldn't have even
Yeah,
imagined, right?
yeah,
Yeah.
which is great.
Yeah.
So do you have an example of when that's happened to you personally?
Um, that's a good question. Something specific. I mean, in terms of my research group right now, I mean, we're we're designing and discovering really new materials, right? Like things that have never been made before, including like new building blocks for these
Cool.
materials that have never even been made. So when we see other people in academia, even just studying those types of materials, it makes us really excited because they're so new and there's so much potential, and we haven't even unlocked like a fraction of their potential yet, right? So that's kind of more maybe on the fundamental science side of things. But when I was a postdoc, I worked with a large team of researchers at Northwestern University,
Oh,
and one of the things we worked on there, which is why I work on it now as well, was designing new MOFs for the detoxification of nerve agents specifically. And now, Newmat Technologies, which is the company that's associated with that research, has been making army suits and gas masks with these MOFs that like I worked with and other members of my team worked with at Northwestern at the time. And they're actually in real US Army suits now. Like there's prototypes. You can see the soldiers have like been wearing them and testing them on like simulated battlefields or whatever. It's
right.
very cool to see.
That is so neat. I mean, that's a really difficult theater to think about, but to know that the stuff that you're making is at least in theory saving some people's lives is really cool.
Yeah, I think that that's really exciting. And to see it actually go from fundamental research to something applied, I mean, that's something that can take, 20, 30, 40, 50 years sometimes, right? And that's what I hope for a lot of the materials that we're making in my group at Concordia now is that somewhere, maybe decades from now, we actually see them being applied in real applications. But to see those materials that I was working with, like I said, at Northwestern, even just 10 years ago being applied now is so cool.
Did fifth grade Ashley ever imagine her stuff would be discovered and then put out in the world for use?
Definitely not. No.
No?
No, I mean, when I was younger, I always liked science. I used to love doing like science fair projects. I was definitely a big nerd. But I think I was always just interested, like I was always curious and interested more in like fundamental science and understanding how stuff works. I was
Mm,
never really back then thinking about like doing research or using science to like improve materials or improve processes or to improve people's lives. I think back then I never made that connection.
sure. Do you remember what got you interested in science, or was it just always an innate curiosity?
Um, I think, well, it was partially an innate curiosity, I think, but I think it was just really working on science fair projects with my parents when I was younger. So my parents used to help me quite a bit with my science fair projects. Neither one of them were scientists, although my dad did work at Dow Chemical,
Hmm,
but he was in sales, so not a scientist, but he had a lot of friends who were chemists or scientists because they did still work together, right? And so
I'm sure he must have absorbed some information.
yeah, exactly. He absorbed some of that information, and often actually he would consult like one of his friends who was a chemist about like what should the science fair project be,
Oh,
right? So
that's
I
great.
always had these like really cool kind of, I guess, advanced science projects because of that, right? And
That's
and
so cool.
so um I got to learn a lot of, different things, and I always really enjoyed that. And I think that's where my interest in science started. And then, um, but at that point, I wasn't sure that chemistry was my biggest interest. I was just interested in science in general. And then in my first year of undergrad, I had a really, really, really good chemistry professor. And I think that's when I decided to kind of narrow my scientific focus into chemistry.
Were you undeclared as a undergrad? Did you not have a major picked out?
Yeah, in my first year, I started in just the general, it was called medical sciences program.
Okay.
So you basically take first year biology, chemistry, physics, psychology, calculus, like just first year science essentially.
Mhm.
And then after that, you pick what you want to specialize in.
Cool. Now, was chemistry something that really grabbed your interest, or were you like, this is easier for me than everything else?
Yeah, that's a good question. I think it was a little bit of both for
Uh,
sure. I mean, it was something that like I found easier to understand. I found easier to grasp. I found like to me everything about first year chemistry felt very logical and that I could like work through problems logically without having to memorize a ton of stuff.
mhm,
And because of that, it was definitely the class that I got higher grades in and all that. So
sure.
definitely partially that it just maybe was easier for me, and then partially I just thought it was really cool too.
How'd you do once you got to organic chem?
That's a good question. So, there's a reason why I'm an inorganic chemist, and it's because I was never very strong at organic chemistry.
That's hard.
It's hard. It's hard, and I can understand why so many people, say that it's one of the hardest courses they've taken in undergrad, and especially really hard for people going into medicine and all of that, right? But I always still really liked it, and
Yeah,
I did okay in it, but I found it difficult. All the reaction mechanisms and also trying to memorize named reactions, all those things was a little bit tricky.
yeah,
Yeah.
yeah. Being able to work through things logically versus memorization, it's two different compartments of the brain that all don't always get the same amount of attention.
Exactly. Yeah.
Um, so you're obviously researching some really cool stuff right now. Does that count as your service to the university?
No, it doesn't actually. So,
Okay.
yeah, that's a good question. As I said at the beginning, most professors at most institutions, although it might vary depending if you're at like a extremely research intensive institution versus a very teaching extensive institution, the percentages will vary. But most researchers, especially in Canada,
Mhm.
um, the job is divided into thirds. So it's 30% research, 30% teaching, and 30% service. And so the 30% research is kind of what we've talked about so far. But the 30% service is something totally different. So it's for example, some of the service that I do is reviewing all of the potential grad student candidate applications that come into our department.
Oh
Right?
boy.
So, like, over the last, few years, I've probably reviewed somewhere slightly over 100 applications from potential grad student applicants from all around the world,
Yeah,
um, and my job is to, first of all, look at their grades and also, compare because, people in different countries, the grading systems are different,
sure.
so comparing that and then looking at their research experience and
Oh man,
their CV and reading their statement of purpose and basically deciding who gets to be admitted into our graduate program versus who doesn't.
that's not easy.
No, it's not. It's definitely not. And that's one thing that a lot of professors have to do. This type of service. That's just one example.
Yeah.
Um, Another example would be like hiring other like new professors, right?
Okay.
So um, when we have a call for a new professor in our department, or sometimes I have to contribute service to other departments too. So it might even be in physics or biology or chemical engineering. We have to look over around 200 applications from people, who want to be a professor in that department and who have done amazing things with their career, right? They've done a PhD, a postdoc, they've done tons of research, and we have to narrow that down and just pick one person. So,
Yeah, that's also tough.
yeah.
But y- do you feel less bad choosing one professor over another than admitting one student over another?
Yes. Well,
Yeah,
yeah, both of it's hard actually because both of those people in their own separate ways have worked really hard to get to the stage that they're at,
that's
right?
true. That's
And
true.
both of those people are going to be disappointed in the outcome if the answer is no, right? So it
Yeah.
might actually be kind of an equal, an equal
Oof,
feeling.
gosh, that is rough. Well, yeah, I mean, a difficult task that is definitely a service.
Yeah.
Um, so what classes are you teaching?
Yeah, so that's a good question. So I always teach Chemistry 241, which is an inorganic chemistry one course. So
Okay,
it's the first level of inorganic chemistry that students will ever see at any level, actually, because inorganic chemistry is not taught in high school or
right.
below the university level. Um, so that course, we teach all about basically all the elements on the periodic table except for carbon and hydrogen.
Oh,
Right? So car- carbon and hydrogen, those are organic compounds, but
yeah,
every other element on the periodic table, that's an inorganic compound, right? So
really?
yeah,
So even like, well, yeah, I mean, I guess I'm thinking about the building blocks of life, and I think carbon, hydrogen, but then like nitrogen,
yeah,
oxygen, phosphorus, and
phosphorus,
sulfur.
yeah, yeah, those are
Eh,
inorganic compounds.
really?
Exactly. Yeah. Yeah. So
Okay.
we teach all about the chemistry of those compounds. We do focus quite heavily on the transition metals. So
Okay.
metal-based materials tend to be a heavy focus in first year inorganic chemistry courses. So we do
Uh
teach
huh.
about that. But yeah, that's the main course I teach, and then I teach upper level courses as well. So I teach courses that are cross listed between 400 and 600 level. So that's last year of undergrad and first year of grad school. So the students are mixed in the same class.
Okay.
And I teach one on the topic of porous materials because that's what I
Yeah.
work with. Metal
Right.
organic frameworks are porous materials. And then I teach another one on the topic of green chemistry. Um,
Okay.
because I think that that's really important to be teaching our students. And it's something that's not in a lot of undergraduate curriculums right now, although it's starting to become more popular.
Can you define green chemistry?
Yeah. So green chemistry is more of a philosophy than a
Okay.
chemistry.
Okay.
So it's a way of thinking about chemistry
Yeah.
to make things more sustainable, more environmentally friendly, and to
Okay.
make sure that we're not harming the environment in the process of doing chemistry. And
Sure.
also it also is to make things inherently safer, right? So that
Yeah.
workers are also safer and people living around chemical plants can
Yeah.
feel safer as well.
Okay. So yeah, that's what I first went to when I thought green chemistry, but then when I get customers talking about black liquors, I'm like, well, I know that that's not a really dark whiskey. That's something different.
I would have guessed that it was a really dark whiskey. So
No, no, it's a very specific um it's a very specific fluid that I don't know enough about, but I know it's not it's not like a consumable you pull off the shelf.
okay, interesting.
Yeah, so uh there's a lot that I need to learn. So if you were to recommend to someone who is curious to maybe think about going back to school for chemistry, how what sort of resources would you direct them to kind of get their feet wet or start getting up to speed for when they do apply as an undergrad for somewhere?
That's an interesting question. I mean, nowadays there you can find pretty much everything online, and you
Uh-huh.
can find excellent online resources, like even online lectures from professors at universities all over the world. A lot of those are open access now.
Yeah,
Um, you can find a lot of open access textbooks as well. So I would just recommend not any specific resource per se, but I would just recommend like even going on YouTube and looking at
sure.
lectures, just making sure they're from reputable chemists and
Uh-huh.
look up their background, make sure they have a PhD in chemistry or that they teach at a university or a college or something.
Okay.
And anything they could, because that could be, you could watch fundamental chemistry lectures, or you could watch lectures on of chemists talking about their research at a higher level, things to just get you interested in chemistry. I think any of
Yeah.
that would be good preparation for to see if you're interested, passionate about it, and if it's for you.
I have heard that MIT has a lot of their undergrad courses just out there and available.
Yeah, I've heard that
So,
too. And I've never looked to see they must have some open access chemistry lectures as well, but I've never actually looked to
well,
see
you sound a little busy, so I wouldn't be too concerned about it. But
that.
when I was applying for school, chemistry, I had two paths to go, and chemistry was one of them. And I did not choose the chemistry path, so I haven't done any real chemistry learning in almost 20 years. So
Wow, okay.
I'm going to, I think I might dive back in just to be able to better educate myself about everything that UIC does and the people that I'm talking to, because I love being able to hear what you have going on and your mocks and your research and your students. But I wonder if I can ask better questions if I'm better informed. At the same time, my level of ignorance might be just right for hitting a wider audience.
I was gonna say sometimes it's good to ask, I don't know, like simpler questions or bigger picture questions. I think oftentimes professors and researchers also just discuss a lot like amongst themselves or within an academic community. It's also good for us to practice talking about our research on, a bigger picture level and without so much detail, but with still being able to communicate what we're doing.
Well, that brings up a good question because I know right now is a time where a lot of folks are applying for or waiting for their grants to come in. The the grants that you have to write, the people who are reading these and releasing these grants, are they typically people who are uh, deep within your field, or are they someone who might not have any knowledge of your field?
Yeah, that's a good question too. It varies quite a bit. So the answer to your question is that it can be both essentially. So it
Okay.
depends kind of what agency you're applying to or what specific program you're applying to.
Sure.
Oftentimes grants get sent out to external reviewers, so not necessarily people working at the government agency or whatever funding body, but to external reviewers. And usually the agencies try to pick external reviewers that are within the field, right?
Okay.
So usually when I submit a grant, they will try to submit it to external reviewers, so professors or researchers in industry who are working on MOFs, right?
Okay.
But usually they'll try to do. But but sometimes they won't. Sometimes the external reviewers could be any scientist that has any sort of working knowledge of chemistry, right?
Okay.
And then the agency or the committee at the agency or whatever will take all those external review reports. Usually there's anywhere from two to maybe upwards of five or six, and
Yeah.
they will read these external reports and then decide whether you deserve funding or not. So
Okay.
oftentimes the people making the final decision are not in your field.
Okay.
Usually they have some sort of science background, but not
Okay.
necessarily in your field. But they just read these external reviewer reports and make a decision based on that.
So, what was your most recent grant request revolving around?
That's a good question. I've written so many grants this term that
Oh boy.
I'm trying to think of which one. I think this term is a record for me. I think I've submitted 11 grant proposals, which
Holy cow.
usually each term I submit a maximum of two, but this term I'm not teaching, which is very, very rare for me.
Okay.
So I decided to try to do as many grant proposals as possible. So
Sure.
I'm trying to think. So one of the ones that I just recently submitted. So in Canada, we have a lot of funding programs for academic researchers to work with industrial researchers. That's like
Okay.
a big push right now by our federal government funding agency, right? So they want instead of funding fundamental science research. They want, which they still do some of, but arguably they should do more. Uh, but they're interested in funding really applied research. So academic researchers partnering with industrial companies. So recently I submitted a grant application where it was 6 professors in total,
Okay.
collaborating with 2 companies here in Quebec.
Okay.
And they're specifically companies that are in the mining industry, so
Sure.
hydrometallurgy, and like, so they do things like how, like, the things that they're interested in is how to first of all extract elements from the minerals, the way that they're found in the environment,
Uh-huh.
and then once you extract those elements from those minerals, also how to separate them from each other to get like pure versions of those elements, right?
Sure.
So one of the grant proposals I submitted recently, like I said, 6 professors in 2 companies, some chemists, some chemical engineers, and we're trying to use, well, metal organic frameworks, the materials I work with,
Uh-huh.
but also lots of different processes and methods that have been developed by the other professors on the application
Yeah.
to try to find new ways to separate those different elements from each other that are more sustainable,
Okay.
ideally. Because right now the methods tend to use a lot of acid, they use a lot of solvent, they produce a lot of waste, and
Yeah.
that waste is, pretty nasty waste if you think about it being organic solvent and acids and stuff. So
Yeah.
trying to find more sustainable ways to do that.
Um, Now, this brings me back to our conversation earlier about the academic papers. And you're like, wow, I never thought about stuff being used that way. Is this, are these mining companies in this project, is this what you had in mind for the UIC kilometer?
No, it's not
Oh, okay.
actually. So this, I should have talked about that one actually. So
No,
for
I mean, don't worry about it. I'm not here to push UIC. I want to learn about you. But if you're willing to talk about UIC, then by all means, go right ahead.
I like it. I like the mug. No, definitely. So I should talk about that project too, because I also submitted that grant proposal, but that one was submitted in the summer, so just before this term. So it's not
Okay.
quite as fresh in my mind. But
Sure.
that is also an academic industry partnership. So
Okay.
it's with a company in Quebec called Deep Sky.
Cool.
And Deep Sky is a company, they're pretty new actually, but they're trying to basically revolutionize the carbon capture industry. So I think, I'm sure I won't do it complete justice. Somebody from Deep Sky should really be the one saying this, but I
Well, I'll
think
have to reach out.
yeah, you should. I think that their main thing is that they believe that research on carbon capture and basically research in regards to fighting climate change and reversing the global increases in temperature that we see is moving too slowly.
Mhm.
We've made, of course, a lot of progress, but we're also getting closer and closer to what some people would call doomsday, right? Where the planet is actually no longer going to be sustainable for us to live, right? So their goal is to increase the speed at which carbon capture research is conducted. So they have a huge network of academic researchers, industrial researchers, and they bring people together, bring teams together to share their resources and their knowledge, better than scientists are already currently doing that. And they provide funding, of course, to do that, so that we can try to accelerate this carbon capture research. And so part of what I'm working on with Deep Sky is using MOFs for carbon capture. And then, of
Mhm.
course, if we're going to use MOFs for carbon capture and we're going to test them in my lab, like I said, in my lab, we do small scale stuff and we make simulated solutions or simulated environments. Um,
Mhm.
we're going to need to measure the carbon in our samples and
Yeah.
see how much carbon we take up versus how much carbon gets left behind. And
Sure.
that's where I was thinking about what type of instrument we would need to be able to do that. And I was just Googling total inorganic carbon analyzer and
Great.
seeing what companies provide it. And that's when I found UIC, and
Well,
it seemed like the instrument does everything we need. So,
yeah, that's that is awesome, and that provides me with a lot of great information too.
well, good.
Um, so because we're here getting into nuts and bolts about stuff, how much does bench space matter to you when you're working in the lab?
That's a
The,
good question.
the question behind the question is how how much do you want our machines to shrink? Or is that like not really a huge concern?
It's definitely a consideration, but, like,
Okay.
obviously within reasonable limitations, right?
Yeah.
So, obviously, lab space is always precious.
Hmm.
What professors, I think, especially professors in chemistry, but probably any scientist will always tell you is that universities never have enough space and
Of
researchers
course.
never have enough space, and people
Yeah.
are always fighting and arguing about space, right?
Yeah.
It's like kind of universal everywhere, right?
Yes.
And it's definitely true because I'm a fairly new faculty member at Concordia. Like I've been there for 6 years now,
Hmm.
and even in those 6 years, I was given what at the time was considered, a pretty big space, right?
Uh-huh.
But in those 6 years, we have really filled out that space, right?
Yeah.
10 students, all of their equipment and supplies, all of the equipment we need to run our group. Suddenly the bench space all gets taken up, right? So
Uh-huh.
it's important. I mean, I think at the end of the day, if there is a piece of equipment that does absolutely everything you need and it's perfect and it has all the specs you want, but
Yeah.
it's a little big, I don't think that that's going to prevent you from buying it. I don't think it's going to be the one thing that prevents you. But I
Okay.
think if it's smaller, it's a bonus.
Okay.
Yeah.
Yeah. Uh we were doing R&D on a new model, and like the titration of the cell just, it was over titrating. We're like, is it a heat issue? Is it from the electronics inside? And I just wanted to keep saying, like, can we go a little bigger with the case? Can we just a little bit bigger? But we've got some really smart guys who have figured it out. So uh yeah, it's but that project is on hold, and it's exciting for when that will come around. But yeah, it just got me thinking, like, how big can we go to make some of these things easier?
Yeah. I mean, yeah, it's a good question. I think there's a limit obviously, but
Right.
there's also a limit where size can't limit, accuracy or other things like that.
Yeah. Yeah. I interviewed a couple of oceanographers about a month ago, and just hearing about living on one of these ships for like a week or two, and with you've got undergrads, grad students, postdocs, plus the actual researchers, plus the ship crew, and like you're working all day. That sounds like a very tight space.
Oh, for sure. And they definitely, they need like a lot of different portable instruments too. Like their
Hmm.
criteria are going to be very different than most of the rest of us. But yeah,
Yeah.
I always think that's really cool too. I'd love to do some research on a ship. I got to find some excuse to do that.
Well, maybe I can try and hook you up with the folks I interviewed with, because they seem so welcoming and so friendly. Um, maybe there's a application for a moth in seawater.
Yeah,
Microplastics, maybe.
yeah, I mean, there could be. There definitely could be. I mean, microplastics, the way I tend to think of it, but I might have a naive understanding, but they're microplastics or they're micro size. So they're kind of big, right? And the pores in our moss, the pores or the holes in our sponges, they're like 3 nanometers
Uh
in
huh.
size is kind of like the biggest. So I
Yeah.
think, microplastics aren't going to fit inside the tiny pores in our materials. I think you need like bigger pore materials than the types of stuff I'm making. But I don't know. I mean, I'd
Mm.
like to talk to people who actually are experts in that and see. Maybe you never know. I'm always surprised by the things that moths can actually do when you start talking to people who are experts in the application side.
Well, yeah, I'll give you their info. I mean, they invited me out on a cruise next October, and I'm like, absolutely, I would love to go check it out.
That's so cool. Where are you going?
Right. Uh, Bermuda.
What?
Yeah, in October. You can't beat that.
That's so fun.
Yeah. Well, I mean, we'll see. I would very much hope that all of this follows through and gets to continue. Um, but it was an extremely generous offer, and I would go down there with the camera and film everything that was going on, and then also get my hands dirty and pull up some chains and uh, extra. I mean, I don't know if I would want to handle any of the samples, but I'd be happy to pull up cable and chain and do all the heavy lifting that the undergrads have to do.
That's so cool. That would be a really awesome experience. So.
Yeah. Um, so, what are some things that students get really excited about in your lab?
That's a good question. So it varies a lot. So there are some students who get really excited about, the fundamental chemistry, right? So if they the moment they make a new material, right, they get super excited. They see the crystals under a microscope, right? And you can see like crystals, have this perfect morphology and they look beautiful under a microscope or under a scanning electron microscope. And so I think one of the things my students some of them get really excited about is when they finally make this material that they've been, we hypothesized it, we designed it, we know what we want, but we don't know exactly how to synthesize it yet, right? And some of them it'll take 500, 600 reactions
Oh,
that they have to put together to be able to make it. And so imagine, you know, you've spent months putting together these 500 and 600 reactions, and then one day you put that sample under a microscope and you see the exact morphology of the crystal you want. I think that's super exciting. I know that that was always really exciting for me, and I know that students get excited about that too.
can
We
you share any of those images, or is that all like
No,
proprietary?
no, I could share some of those with
Okay,
you.
great. I think it would be cool to have the crystalline shape be the cover for this podcast interview.
For sure. Yeah, let's do it. I will definitely send you one. Remind me in case I forget. I have a bad memory. So
Okay. So 500 reactions. Is it just tweaking the levels of everything to get there?
exactly. Yeah. It's like
Oof.
tweaking the parameters. So it's like the solvent, the temperature, the time, the pH, sometimes like little additives, sometimes even the amount of time that it reacts, right? Some reactions only take a few hours, some take a few days. So it's like systematically tuning all those parameters until you get the get the exact ones you need to make the material we're looking for.
That is awesome. And then you've got to be excited when they're excited.
Oh, I'm so excited. I mean, one of the most exciting things is when somebody in my group makes a new muff. Like, I can't even describe how excited I get about that. It's like, it's crazy. It's like I just won the lottery,
Sure.
because it's, first of all, it's cool to see their excitement, but also I just think it's such a cool thing in chemistry to make like a molecule that's new that nobody's ever made before. Like, think about how crazy that is and how people have been working in chemistry for like, hundreds of years or even more, depending on how far you want to go back in history, I
Sure.
guess. But and you still to this day can make like new compounds or molecules that nobody's ever made before. That's so cool.
So that has to be extremely rewarding. Can you think of any one particular moment that has been like the most rewarding experience of your career?
Ooh, that's so hard to say.
All right.
Um,
Well, if that's too hard, can you think of one of the most challenging experiences?
Ah, so I think what's most challenging, maybe it's not exactly the way that you or maybe thought the question would go, but one of the most challenging things for me as a professor and as it relates to mentoring students is like knowing the best way to mentor students and like what the expectation should be sort of or how I can push them to be the best scientists that they can be but without pushing them beyond some like crazy boundary that they're overworked or that they're burning out or whatever, right? And it's like it's finding that balance that I think is extremely hard as a mentor or as a professor, because of course we want our students to be the best, right? And we want our students to be super successful. Like we want them to come out of our program and out of our research group like knowing everything they can possibly know and having like a network of people who they've already met and can work with once they leave our institution and our group. And we want them to have, accomplishments on their CV, like papers, and show that they've gone to conferences and presented stuff. And we want them to be the best, but at the same time, like, you have to be realistic, right? We also don't want them to have to work like 80 hours a week to be able to
Yeah,
accomplish those things, right? And to get totally burnt out and exhausted by it. But I think as a PI, it's always about finding like the balance. Like, you want to push people and encourage people to be the best, but not overdo it. And it's hard to find that balance, especially because that balance is different for every single person. And
sure,
so, in addition to being a scientist, we have to be like a social scientist as well. Right?
sure.
Yeah.
Well, if any of them ever need practice prepping for a presentation, shoot them over to the UIC podcast, and
That's
I'd
true.
happily talk to them.
That's true. I'm sure some of them would love to do that.
So, what are you researching right now that you're most excited about?
Oh, that's tough to pick like the thing I'm most excited about.
Oh,
I
then a couple.
I think one of the projects I'm currently most excited about, maybe just because it's fresh on my mind, because I was just talking to one of my students this morning, is we're trying to make new flexible metal organic frameworks. So all MOFs are flexible in some way. You can think of a porous material with a bunch of holes in it, like it's going to have some degree of flexibility, right? But you can design MOFs to be even more flexible, right? Where you can design the materials such that they have like a closed pore form and an open pore form, where when they're exposed to different guest molecules or different external stimuli like temperature or pressure, or maybe exposure to carbon dioxide for carbon capture purposes, that maybe the moth has closed pores, but then it sees carbon dioxide and the pores open up. And all of a sudden,
Whoa.
the material flexes and it absorbs like a very high amount of carbon dioxide, but only does that sort of flexing in the presence of that one guest, right? So it's selective for only absorbing one thing. And so that's probably one of the projects I'm most excited about right now, because my student actually just this morning showed me some data that suggests she may have made a new metal organic framework.
Cool.
I don't want to get too ahead of myself, but it looks like it is. And it looks like it should be really good for gas separations because of potential flexibility.
Now, again, not a scientist, just a enthusiast and a sci-fi writer on the side. Could you take a material like this and make grates out of it, and then stack those grates in some sort of exhaust flume, and then it would be capturing a lot, or is that totally inefficient and
No,
ridiculous?
I think what you're describing can totally be done. I mean, I think that is what some people are doing. I mean, Svante, I don't know if you ever heard of Svante. They're a company in Canada right now that's using MOFs for carbon capture.
Yeah.
And they've started making the reactors basically to be able to do that. And, of course, a lot of engineering goes into this too. And that's also beyond my understanding of how things work. But they've made these kind of cool, like, I guess you would almost call them plates that they put
Hmm.
the MOFs on in these reactors for carbon capture. It's not
Yeah.
so different from what you just described, I don't think.
Cool.
Yeah, so
Awesome.
it's possible.
Um, do you like to explore the ideas of application for these things?
I do, yeah. So, I mean, I always have to, make sure I know my own limitations, right? So,
Uh-huh.
which I think is important for all scientists.
Okay.
So, my expertise is like definitely on the design and synthesis of new materials, characterizing them, and maybe doing like the most basic application testing, right? Like just to
Sure.
see, does the material absorb this, or does it sense this, or can it separate these two gases? Like we can definitely do those things, right?
Yeah.
But when it comes to actually truly applying a material, there's so much more that goes into it, right? Like
Yeah.
materials performance, which is what we do, and synthesis and performance is of course a very big aspect. But then there's so much else, right? So there's process chemists that have to work on ways to scale up the synthesis of the materials. And then there's engineers that have to work on ways to formulate the materials. Like sometimes you pack them into, little cubes or discs or whatever. That's all done by engineers. And then there's of course people making like the reactors or whatever for the process that you need. There's a lot that goes into all that. So I always make sure that I'm partnering with people who know what they're doing.
Yeah.
So I partner with a lot of people in industry, right? And a lot of our funding comes from industrial partners in some way, or from, like I said, the Canadian government will also support partnerships like that. So I'm certainly very interested in the applications, and I love seeing our materials being applied for something or being tested for something at like a bigger scale, right? But I never want to oversell that, I'm not an expert in any of those applications, really. I'm an expert in the materials design and testing.
Well, I am an expert in being wrong and getting rejected. So I like throwing wild ideas all over the place and being told, no, you can't do that. No, 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 it doesn't work that way. I'm like, okay, cool. It doesn't bother me.
I don't know. Having wild ideas is good though, because all you need is one wild idea that ends up being a really good idea,
Right.
right?
Right. So what are your hopes for like the future of your research and your MOVs?
Yeah, that's a good question. So, I mean, I think my hope is that, well, first, that we continue to, do a lot of fundamental research and that we hopefully get supported by that, both in terms of funding, but also in terms of the academic community. So, you know, discovering new materials, designing new materials, testing them in the ways that we can test them in our labs at Concordia. I think that's a lot of what I hope for, kind of on the most basic level, and that the students can continue to learn like all the different transferable skills that they can learn through doing that type of fundamental research. Um, but I think, the pie in the sky sort of dream goal is that these materials that we're making in my lab at Concordia, that we're the first ones to have ever made them, and we're the ones putting them out there in the literature and in patents and whatever, that one day somebody finds an application for them that is amazing, and that helps people in some way, whether it be by like cleaning up the environment or protecting soldiers or yeah, or just making an industrial process more sustainable, more environmentally friendly, anything like that. I mean, that would be the dream goal. And like I said, in most of chemistry, that takes like decades to kind of realize that, right? But hopefully that's what happens.
Well, it sounds like you're already getting some of that with your Northwestern research.
Yeah, definitely, which is really exciting. I mean, that's a really amazing team. They're one of the best MOF research groups in the world, if not the best. Maybe I'm a little bit biased, but um, so they're doing really impressive stuff, and they're managing to accelerate that time between fundamental research and applied research, and it's really cool.
That's awesome. Well, I think that everything that you had just described is really exciting, and uh, it's these moths sound so cool.
I'm glad you think so.
Yeah,
Glad you like them.
absolutely. Um, well, what where can people learn more about you, your work? If you had a high school student who is interested in reaching out and picking your brain, or a scientific publication or a journal or whatever, it was like, oh wow, I'd love to learn more about this. How can they get a hold of you?
Sure, that's a good question. So there's a few different things they can do. So first, they could even just look up my name on YouTube. I have like 4 to 6 kind of like videos or video lectures where I describe more about my research, and some of them are even like one's like a lab walkthrough tour where you can also
Oh,
see my lab and see all the
awesome.
equipment
You
and
got to
stuff.
send me a link. We'll put it in the
Yeah.
show notes.
Yeah, I could definitely do that. That's cool. Those videos are useful if you want to learn more about our research and actually see kind of more visuals related to it as well.
Yeah.
And then you could also go to my website. It's thehowarthlab.com. And on there, you'll also find my email where you can email me and contact me directly. But there you can also see all of the students that work in my group. There's photos of
Right.
them and little bios, and also you can see all of our most recent publications. Some of our publications, especially most of our most recent ones, are open access. So if you click on
Cool.
the links on the website, you can go directly to our papers.
Great.
And you can also find me on Twitter or
Okay.
X, I guess. Um,
Yeah.
I'm not on there quite as much as I used to be, but I'm still around. My Twitter handle is Chem Ashley, and so you could follow me there. And sometimes I post updates on like our latest research papers or my students' latest accomplishments, stuff like that.
Well, I'll give you a couple follows as soon as we're done.
Awesome, thanks.
Yeah. Uh, Great. Is there anything that you would like to leave our listeners or viewers with before you go back to researching?
I don't know. I don't know if there's anything specific. I mean, maybe just I hope that from listening today, they've learned a little bit about metal organic frameworks and the different types of things they can do. And I hope I've piqued some of their interests, and maybe they can do some more research on the subject themselves. And if they're interested in science at any level, they can contact me. I'm always happy to have undergraduates, graduates, postdocs, whatever, working in my lab, and I can teach you everything about moths.
Awesome.
So, yeah.
Cool.
Yeah.
Well, thank you so much for the conversation this morning.
Yeah, no problem. Thank you for having me. It's been great.